Let us look at one of the most efficient algorithms for sorting known as QuickSort. You have already seen an introduction to QuickSort where we use linked lists to demonstrate the idea of partitioning and how we avoid merging in QuickSort. In this lesson, we look at the original version of QuickSort which was proposed by the well-known scientist C.A.R. Hoare, and how by doing QuickSort in an array and partitioning the array in place, we get the best possible in practice performance. QuickSort is famous for its average case performance. So just to review, we are quite familiar with the sorting problem by now. We are given an array of n elements and the objective is to rearrange the elements of the array in ascending order. And we have seen the brute force search algorithms such as selection sort and bubble sort, which gave us O(n) squared complexity. We have also seen a more efficient divide and conquer algorithm, namely merge sort, which gives us n log n complexity. QuickSort gives us the best of both, in the sense its best case performance is very good. Its worst case performance is not so great, but its average performance is the best, in the sense it is n log n. So QuickSort gives us very good average case performance, although we compromise in its worst case by getting n squared complexity. But because of its very efficient implementation in arrays and its ability to rearrange elements in the array in place, it gives us the best performance in practice when we sort large data sets. Right? The algorithm for QuickSort is rather simple. It's a straightforward implementation of divide and conquer. So we are given an array where the data elements are from low to high, and if low is less than high, that means the problem is not small, right? So if low is not less than high, that means there is only one element and there is nothing to be sorted. Then we call another algorithm called partition. So this partitions the array into two parts. It returns the partitioning position j. Then we call QuickSort recursively on low to j minus 1 and j plus 1 to high. This can also be implemented without recursion. We will see that in the next lesson. So we call QuickSort recursively on the first part and the second part. This is a classical divide and conquer structure. But the important thing is, after sorting the two parts, there is no need to merge the two sorted arrays. How is that possible? That is possible because of the way partition works. So we will see how partition works. But before that, let's look at an animation of QuickSort. So here, the height of each line indicates the value of the data element being sorted, and as we will just observe it for a minute, and then I will explain how partitioning works. Alright, it's sorted now. So let's now start. Right? It assumes that the first element is what is called the pivot. And then it rearranges the elements so that every data element which was less than the pivot, right, comes to the first partition. And every element which was greater than the pivot goes to the second partition. You see that happening. So all the elements in this first part, right, are less than the pivot. All the elements to the right are greater than the pivot. When that is done, right, there is no need to merge the results because all these elements are less than or equal to those other elements. And the same thing is happening recursively over and over again. Right, so let's see, complete this round, and then we will trace the pivots for a couple of recursive calls, and then we will understand how this in-place partitioning is working. Right? So again, we start with this as the pivot, and then we keep exchanging elements to move all the taller lines to the right and all the shorter lines to the left. So the left partition has all the short guys and the right partition has all the tall guys. And then we repeat that process. The red ones are all the pivots that are being selected to partition the array further and further down until we have just a one element array which doesn't need any partitioning, right? So that's how QuickSort works. So the idea of QuickSort is it's a divide and conquer algorithm. The purpose is to avoid having to merge the two sorted arrays after sorting the two subarrays obtained by dividing the problem. How do we do that? How do we avoid merging, right? So the idea of partitioning accomplishes that. And what it does is, the way it breaks the array into two parts is such that every element in the first part is less than or equal to every element in the second part. If that is the case, I can simply leave them in place. There is no need to even concatenate because they are all in the same array now. And that is accomplished by the particular element chosen, which is called the pivot. Your textbook by Horowitz and Soni doesn't use this term pivot, but it's a very common term used in the context of QuickSort. And normally, we simply take the first element of the array as the pivot. If you want better performance, you can take some other element or use randomly select the pivot. And so there are various versions of QuickSort. We'll look at the simpler version where we simply take the first element of the array as the pivot. So the real crux of Hoare's version of the original QuickSort algorithm, which gives us the best performance, is in its partition algorithm, right? And what it does is, it takes the array which goes from low to high minus 1, right? And there is one extra element, and this element is set to a value greater than all the other data elements. This is just done so that we don't have to check for array boundaries every time when we go through a loop, right? So it's normally denoted by infinity. It's just some number greater than all the other elements. For example, if the data elements are all Sachin Tendulkar's batting scores in cricket matches, we know that nobody can score 1,000, so I can set this extra element to 1,000. Right? And then we take this first element as the pivot, right? So pivot is a low. Then we have two pointers, I and j. I is set to low and j is set to high. Okay, so I is set here, j is set there. Then what happens during this algorithm is I moves to the right, j moves to the left. And as they move, I moves until it finds an element which is greater than the partitioning element, the pivot. So I is I plus 1. Move to the right until you find an element greater than the pivot, greater than or equal to the pivot. Similarly, j moves to the left until it finds an element less than or equal to the pivot. Why is it doing this? Because if you have an element greater than the pivot, it belongs on the right side. So it should be switched to the right side. If you find an element in j that is less than or equal to the pivot, that belongs in the left partition. So that should be moved to the left. And we do that by swapping ai and aj. So if you find a particular element here and a particular element here, this one is greater than or equal to the pivot, this one is less than or equal to the pivot, we interchange them or swap them. So when you swap them, you keep doing that. Again, after swapping, you move I and j to the right. So there is a repeat until loop until when I and j cross each other. So when I goes beyond j and j comes to the left of I, we stop. That means the partitioning is over. At that point, what we do is we swap or exchange the pivot with the position where j was. So a low, the first position, gets aj gets the pivot, and after that final swap or exchange, we return the position of j as the partition. So what this algorithm guarantees is that every element in the first partition is less than or equal to every element in the second partition. And because of that, there is no need to merge. We simply need to sort the two partitions, and we do that by recursively invoking the same QuickSort and partition algorithms on the two parts. Right? So let's look at an example. Right? This is the same example of Sachin Tendulkar's last 10 scores, except I have made a small change. Right? I have interchanged these two data elements. It so happened that Sachin Tendulkar's most recent score, 140, was the highest number. And if we take that, we don't get good partitions in QuickSort. That's one of the problems with QuickSort. It doesn't always give you equal partitions. In fact, it can give you, in the worst case, a partition where one partition has only one element and the other partition has n-1 elements. Right? That is why its worst case becomes ON squared. But to avoid that, in our example, I have just put 22 here and 140 there, just so that we get slightly better partitions. So we are given this array of 10 elements. Let's see how partition works in this. We add an extra element, the 11th element, and we put some very large value there which is greater than all the other elements. We choose the first element as the pivot. So the pivot is going to be 22. I, the pointer, points to the first element. J points to the last element. We start moving I to the right until we find an element that is greater than or equal to the pivot, that is 140. We move J to the left until we find an element less than or equal to the pivot, that is 8, which is less than 22. And what do? We swap these two elements. So we exchange them. So this becomes 8 and this becomes 140. Now we move I further to the right, looking for an element greater than or equal to 22. We found 56. We move J to the left, looking for an element less than or equal to 22. We found another 8. We swap these two elements. So this becomes 8. This becomes 56. Right? Next we move I further to the right. We find 108, which is greater than the pivot. We find 5, which is less than the pivot. We swap them. It is these swaps, these exchanges, that give the high efficiency in the average case in actual practice for this QuickSort algorithm. Now we move I further to the right, looking for an element greater than or equal to 22. We find that here. So I will be pointing here. We move J to the left, looking for an element less than or equal to 22. We find it here. But now I and J have crossed each other, right? So we stop this part of the algorithm, we get out of the loop, and in the end we swap, we exchange the J position with the pivot, that is, we interchange these two elements. So finally the new array that we get would be 2, 8, 8, 5, 9, 22, 76, 108, 56, 140, and this extra element 1000. So in this new array, the pivot is 22. It's not a new array, it's just the same array that has been rearranged. The pivot is 22, right? And the array has been partitioned into a left part where every element is less than or equal to 22, and a right part where every element is greater than or equal to 22. We can sort this left part independently, we can sort the right part independently, and then there is really no need to merge. We can just leave those sorted arrays in their places in the array, because all of these elements are already in their correct positions together. They are all to the left, and all the elements greater than the pivot are to the right, and the pivot is in its correct position. We don't need to do anything about it, right? But notice that these two arrays are not already sorted. They have only been partitioned. They get sorted when QuickSort calls itself recursively. For example, when you call QuickSort on this, 2 will be chosen as the pivot, and then let's see what happens. It turns out that all the other elements are greater than 2, right? So if you actually execute the same partition algorithm, what will happen is I will start here, it will look for an element greater than 2, which it will find right here. J will start out here, and it will start looking for an element less than or equal to the pivot, which it will find only here. So I and j have already crossed each other at that point, so we can't do any further partitioning. We exchange j with the pivot which is already there. So in the next iteration, in the next recursive call, we get a highly skewed partition where 8, 8, 5 and 9 will be a partition of 4 elements, and 2 will be a partition by itself. This happens a lot in QuickSort, right? There's a 1 and an n-1 kind of partition, which results in its worst case performance of O(n) squared. On the other hand, if we were to partition this right hand side array, so we will take 76 as the pivot. So I moves to the right, finds an element greater than or equal to 76. J moves to the left, it finds 56 as an element less than or equal to 76. So this element belongs in the right partition, 56 belongs in the left partition. We need to swap them, right? So these two get exchanged, and then I moves further to the right, looking for an element greater than or equal to 76. It finds one, but when j moves to the left, it finds it only here. I and j would have crossed, so they get swapped. So eventually you will get 56, 108, 76, 56, 76, 108 and 140, where 76 was the pivot, the left partition had only one element, and the right partition had two elements. So like this, eventually every partition will have only one element, and it's already sorted, and there is no need to merge. At that point, all the entire array is already sorted. So this is how the in-place partition algorithm works in the case of QuickSort, to give us a highly efficient algorithm for sorting large data sets, especially in practice in terms of its average case. Although its worst case performance is still order n squared because of this 1 and n-1 kind of unequal or skewed partitions that can result when the pivot is not ideal for that particular array. So this is how QuickSort works.